Hello, hello, hello. All right, reciprocal function. So looking right away, some of you might say, okay, so x can't be 0. Well, you would be correct. X cannot be 0 because it's in the denominator, and we can't have a 0 in the denominator. Question for you, is there anything that y can't be? Some of you might be saying it can't be 0 as well. Excellent. And the reason is because if I set this equal to 0, is there any value for x that's going to make this equation true? Anything at all? No. So ladies and gentlemen, I would like to introduce you to asymptotes. We have a vertical asymptote at x equals 0. Asymptotes are drawn as dashed lines, and it's an asymptote because it's an undefined value. Okay, we can't intersect a vertical asymptote ever because it's a value that makes our function undefined. Okay, so we don't exist there. And then a horizontal asymptote at y equals 0. Sometimes you can interact with a horizontal asymptote, and we'll see this with rational functions, but for the reciprocal function, you cannot. Okay, the purpose is to simply guide the end behavior of your function, and the vertical asymptote will guide it as well. Okay, so sometimes you will see that the asymptotes are on the axes. You can do what I did and extend it out, or you're more than welcome to draw it a little bit above or below or to the sides. So let's go ahead in our chart and just write in the asymptotes because we know they exist now. That's awesome. All right, parent function points. Every function has them. For this one, we're going to say that x is -2, -1, and -1/2. And then 1/2, 1, and 2. Okay, so if we plug in -2 to the function, we get -1/2. -1 gives us -1. If I plug in -1/2, that's 1 divided by -1/2. So 1 times its reciprocal, so we get -2. If we plug in 1/2, we get 2, 1, and 1/2. If you struggle with that idea, definitely write it out. Okay, so you can see it. So -2, -1/2, -1, 1, and then 1/2, 2. And ladies and gentlemen, there is your reciprocal function. It's cute. Okay, so our HK is 0, 0. There isn't an x-intercept, nor is there a y because we have asymptotes on the axes. Okay, domain. So if you're using set notation still, you can say x is less than 0 and x is greater than 0. Or we would say that -infinity to 0 non-inclusive, because we don't exist at x equals 0. And then union 0 to infinity. The union just symbolizes that there's two pieces to the domain, and you put them both together for the function. They both exist. Okay, range, very similar. Y is less than 0 and y is greater than 0. Or -infinity to 0 non-inclusive union, non-inclusive 0 to infinity. Excellent. Okay, so increasing and decreasing intervals. As we go from left to right, where do our y values go? Even on the second piece. Yep, everything is decreasing. This function isn't going to do both. Okay, so we're not increasing on the parent function, we're decreasing with our domain values. -infinity to 0, union 0 to infinity. Is it 1 to 1? Yes. The rate of change varies. And even though there is a line of symmetry, there isn't an axis of symmetry, and we don't have minimum or maximum values. All right, so there is our reciprocal parent function. Okay, let's take a look at this example. There might be a b value that we'll come across, so let's write that out. A is in the numerator for this function, b is in the denominator because it affects the x values, and k is on the outside. So looking at the example, I can see that we do have an a value. A is going to be -1, which means we're going to get to see a vertical reflection. The quadrants that the little pieces are in are going to shift. There isn't a b other than 1, so there isn't a horizontal stretch, compression, or reflection. H is 8, so we'll go 8 units right. and k is 3. So we'll go 3 units up. Okay, setting up our transformation chart. If b is 1, then we're just going to have x plus 8 and negative y plus 3. Okay, so for our asymptotes, we know that, well, let's look back at the parent function. If we look back, where did the vertical asymptote come from? Yes, it's the value that makes the denominator undefined. So for our vertical asymptote, we can take x minus 8 and set it equal to 0, and we can see that x is 8. So that's going to be our vertical asymptote. We can draw that in and write it in our chart. And then I'm just going to tell you that k is your horizontal asymptote. Now, some of you might be thinking, wait a second, h is our vertical asymptote. And I would say, yep, nice job, you're right. So we can go ahead and write that. And this is reciprocal function only. As we get to more rational functions, that will not apply, okay? So the horizontal asymptote is always y equals k. And the vertical is h. Whoa, is x equals h. Nice job if you saw that. All right, so let's find the points. Here we go. I'm going to, because I can't see on my screen, write the parent function points next to it. We have negative 2, negative a half, negative 1, negative 1. All right, plugging in. Negative 2 plus 8 gives us 6. Negative 1 plus 8 gives us 7. And then negative a half plus 8 gives us 7.5. For the y values, if I plug in a negative 1/2, the negatives cancel each other out. So we get 3.5. And then negative 1 gives us 4. And negative 2 gives us 5. Okay, back to the x's. 1/2 plus 8, 8.5. 1 gives us 9. 2 gives us 10. And then if you plug 2 in for y, we get 1. Plug in 1, you get 2. And then plug in a half, and you get 2.5. Nice. All right, let's graph it. So then 6, 8, 7, 6, 3.5. And then 7, 4, oopsies. Oh my gosh, sorry. There we go. And then, oh my goodness gracious. And then 7.5, 5. Okay, and we'll connect them. My points are closed, you guys, but I know they look open because it's so touchy right now. 8.5, 1, 9, 2, and then 10, 2.5. Excellent. There it is. Okay, so our HK we already defined to be, oh, goodness gracious. Go back. Okay, to be 8, 3. And then our x-intercept, ooh, I see one, but I don't know what it is. So we're going to have to solve algebraically, which I know you love so much. It's not hard. 0 equals a negative 1 over x minus 8 plus 3. Okay, so I'm going to go ahead and subtract 3 to both sides. We get negative 3 is equal to negative 1 over x minus 8. And then to get that out of the denominator, I'm going to have to multiply it to both sides. So we end up with negative 3x plus 24 is equal to negative 1. Okay, and then I'm going to subtract 24 to both sides. So negative 3x is equal to negative 25, and x is equal to 25 thirds. Sweet. So you can write it as 8. Oh my Lanta. You can write it as 8 and 1/3 if you'd like. Doesn't really matter to me. I'm going to leave it as 25 thirds, but I am going to write it as a coordinate. And then there is a y-intercept, because if we were to extend that graph out, we'd intersect the y-axis, but we don't know what it is yet. So we're going to solve. So y is equal to a negative 1 over, plug in 0 for x, minus 8 plus 3. We get negative 1 over negative 8 plus 3. So we get 3 and 1/8. Lovely. So 0 and then 3 and 1/8. All right, domain. So we're going to say x is less than h, which is 8, and greater than. Or we'll use interval notation, negative infinity to 8, non-inclusive union, 8 to infinity. The range is restricted by the k value. If you want to write that down, restricted, write it down. These are your notes. Restricted by h. Oh my Atlanta. Restricted by k, which makes sense because h is our vertical asymptote, k is the horizontal. Okay, so y is less than 3 and y is greater than 3, or we're going to do negative infinity to 3 union, 3 to infinity. Okay, we did see a vertical reflection, which means now we are increasing. We're not going to be decreasing. So we'll use our domain elements, negative infinity to 8, union 8 to infinity. Yes, this is 1-to-1. The rate of change varies. Even though we talked about a line of symmetry, we don't have an axis of symmetry, nor do we have minimum or maximum values. Sweet. And there's example number 2, or 1, depending on how you look at it. Your reciprocal function.